Hi, everyone. Today we're going to be talking about organic reactions, and we're going to take a look at some simulations to show how each of these reactions happen. And specifically, we're going to look at reactions with alkanes and reactions with alkenes and alkynes. So I'm going to maximize this screen here, and we're going to first focus in on alkanes, which are all single bonded carbons. And the only type of reaction that alkanes undergo is usually substitution and combustion reactions. So what we're going to do is we're going to take a look at substitution. And you're going to notice that in this column, I have the catalyst that must be used in order to speed up that reaction and how that will work. So the two examples that we're going to talk about, and I'm going to show you a simulation of that as well, deals with methane and ethane. So if I was to draw methane, we know that methane is one carbon with 4 hydrogens all around. What will happen is when chlorine or bromine, which is a halogen, it only works with those two. The other ones are too reactive, like fluorine and iodine. We can add that to methane to get a different type of organic compound. Now, in this case, like they mentioned, you need to have it in the presence of UV light, and we usually write the catalyst over top of the arrow. One of these hydrogens gets substituted. So that's what it means by substitution. One of the chlorines will take its place. And what happens to that other hydrogen and chlorine is that they hook up to form a secondary product called hydrogen chloride. Okay? And so that is known as substitution reaction. Let's take a look on the video how that works.
About the reaction of the compound methane with chlorine. When methane is made to react with chlorine in the presence of sunlight, one of its hydrogen atoms gets replaced by a chlorine atom. The product so formed is chloromethane. If the reaction is carried out with excess of chlorine and continuous exposure to sunlight, the chlorine atoms replace all the hydrogen atoms of methane one by one, giving rise to the products dichloromethane, chloroform, and carbon tetrachloride.
The next example is with ethane. So here's ethane, and again, we will add chlorine to ethane in the presence of UV light. And what we will do is we will substitute. So I will take one of these hydrogens off, let's say, redraw that out. And we hook up the hydrogen that got removed with the chlorine that did not get added. Okay, and that can continue to be substituted as long as you have chlorine available. So that can continue on. So in this case, we got 1-chloroethane, but you could get 1,1-dichloroethane, 1,1,1-trichloroethane, and so forth. So that can continue in terms of substitution. Let's take a look on the video how that works. Now, moving on to alkenes and alkynes, notice that when I printed this, my title got moved down to here by accident, but this should say examples. Alkenes and alkynes undergo a number of different types of addition reactions, and the subcategories of those addition reactions are called hydrohalogenation, halogenation, hydrogenation, and hydration reactions. And we're going to take a look at each of those. Now, the word hydro means hydrogen, and halogen is some sort of halogen from the 7th family on the periodic table. So a bromine, a chlorine, or an iodine in the case of an alkene. So where it has HX, this could be HBr, HCl, HI. Okay, so hydrogen bromide, hydrogen chloride, or hydrogen iodide can get added to an alkene. So what we're going to do is we're going to take a look at an example with propene, and we'll see how that works. And then we're going to also apply something known as Markovnikovs. So let's take a look at this video, and then we will come back and do the example. In this example, we've got propene, which is an unsymmetrical alkene, and we're going to react it with hydrogen bromide, HBr. Now you're going to notice that the HBr can link onto that propene to form one bromopropane or two bromopropane. What we want to do is take a look at which one is the more common compound that is formed. So in this example, you can see that the double bond was between carbon 1 right there and carbon 2. And what will happen is the Br can either hook to the first carbon or to the second carbon. Now, what ends up happening is that first carbon is known as a primary carbocation, and the second carbon in the middle is known as the secondary carbocation. It only has one hydrogen attached to it. So what ends up happening is the hydrogen always goes to the carbon that has the most amount of hydrogens already attached to it. This is known as Markovnikov's rule. So the bromine will actually attach to the second carbon, and the hydrogen will attach to the first carbon. That secondary carbocation is more stable due to a positive inductive effect because it's bound to two other carbons. So what Markovnikov's rule states, which is also known as like the rich get richer, when an unsymmetrical alkene reacts with a hydrogen halide, the hydrogen adds to the carbon that is already bonded to the greatest number of hydrogens. So when we break this carbon-carbon double bond, the hydrogen will go to this first carbon because it has two hydrogens, and the bromine will attach to the second carbon because it only has one hydrogen attached to it. So the halide, the halogen, will attach to the carbon that has the fewest hydrogens, and the hydrogen will attach to the carbon that has the most. In this next example, you can see with HCl being added to one butane, hydrogen goes to the first carbon because it has two hydrogens, it's rich with hydrogens already. The chlorine will attach to the second. Now that we have seen the video, let's go ahead and draw one of the examples so we have it as a reference. So we've got our alkene here, our double bond, and we'll make this propene. And again, this is going to be one propene. Notice that this middle carbon only needs one hydrogen, and this guy needs two. So we saw here that you can add hydrogen bromide. And in this case, we saw from Markovnikov's rule that bromine must be added to the carbon that has the fewest number of hydrogens. And the hydrogen gets added to the carbon that already has the most hydrogens. So remember when we are applying Markovnikov's rule describes the outcome of some addition reactions. And when you have an asymmetrical substituted alkene or alkyne, the hydrogen atom of the hydrogen halide becomes bonded to the carbon that had the greatest number of hydrogen atoms in the beginning. So in this case, this hydrogen will go here and bromine will go here. So you get two bromopropane. Okay. Now, there are a number of different catalysts, and in this case, the main catalyst that I've come across is ether. So again, you would write ether on the top, and then we know that that double bond gets broken, and as we saw in the video, the reasoning for that is due to the secondary carbon having the most positive inductive effect in the stability of why the bromine goes there. Okay, so the hydrogen got added to that carbon, okay, and you get two bromopropane. Whenever you have an alkyne, the same thing would happen. So let's just make one propyne here, okay? So what we would do is if we were to add, let's say, HCl, okay, same sort of thing happens. The H would go to this carbon because it already has one hydrogen. This carbon doesn't have any, so the Cl would go to this carbon, okay? And I'll just draw the products down below. So in this case, there is that new hydrogen that got added. We break the triple bond and it becomes a double bond. Okay, and that end carbon remains the same. So you could continue to add, and if I was to add another HCl, I would just put a 2 in front here, and then the hydrogen would go here, we'd break the double bond and it would become a single bond, and then the chlorine would get added here. Okay, but here I just decided to add one molecule of HCl, but if you had multiple, then you would continue to add. In this case, we've got halogenation. Halogenation is when you have a halogen that gets added across a double bond or a triple bond. And in the case of alkenes, only iodine, bromine, or chlorine can get added. With the alkane, we saw a substitution happens, but in this case, both of the chlorine atoms or both of the bromine atoms or iodine atoms get added. Let's take a look at the video.
The presence of the double bond makes ethene quite reactive. When we add chlorine to ethene in the presence of ferric chloride, the double bond of ethene breaks partially. The two carbon atoms, in turn, combine with one chlorine atom each, thereby completing their valency. The compound so formed is 1,2-dichloroethane, and it is a saturated compound.
Okay, so in the video, you noticed that the catalyst that was used was iron 3 chloride. Another one that I'm familiar with is carbon tetrachloride. And in the presence of carbon tetrachloride with ethene, you add chlorine, and that double bond will break. And we end up with one chlorine on each of the carbons. And so in this case here, you get a 1,2-dichloroethane molecule. Notice this here when you have a triple bond, and when you have a triple bond, this should not be here. When you have a triple bond, you get a transalkene, and we saw that with geometric isomers. So let's see how this works. If I have this scenario here where you've got ethine, and if I'm going to add, let's say I've got iodine being added, one iodine would go here, one iodine would go here, but it would add so that you end up with a transalkene. Remember that trans isomers can only occur with double bonds. So what happens is this triple bond gets broken, becomes a double bond, and you get a 1,2-diiodoethene molecule, and you just put the word trans in front. Okay, let's take a look at hydrogenation. Hydrogenation is when you are adding hydrogen. Now, hydrogen is just that molecule, H2, and we just add that across the double bond. Now, often this happens in the case of when we have hydrogenated vegetable oils in our food. And the reason why they want to hydrogenate them is because hydrogenated foods make the molecules saturated, meaning all single bonds, and therefore they have longer shelf life. But as we've seen in a previous video, and we've talked a little bit about, is the fact that hydrogenated and saturated fats are not good for your heart in terms of clogging arteries and things like that. But let's see how that works in the video.
Is hydrogenation of the vegetable oils. Vegetable oils are long-chain unsaturated compounds. They undergo the addition reaction with hydrogen in the presence of nickel or palladium to form the vegetable ghee that are saturated compounds.
Okay, so let's go ahead and we'll draw a more simpler alkene. We'll just draw our propene molecule here. Okay, and we're going to add hydrogen in the presence of, now in the video they showed that nickel could be used as well. Nickel, palladium, platinum, those are all catalysts. And this enables you to make propane. Okay, so One of the hydrogens goes here, breaks a double bond, the other hydrogen goes here. So both get added, and you now have a fully saturated organic molecule there. And I'll just move that up to make that a little bit better. Whenever you do this with an alkyne, okay, so let's just say that I have this scenario here where I have one propyne and I'm adding hydrogen to it. Okay, what do you end up getting? Well, it says that you get a cis alkene. Now, cis means on the same side. So what I would do is I break that triple bond, and the hydrogen that I'm adding will go up here. This hydrogen will also go up here on the same side. And then this here, I will just sort of move down. So it appears to be a planar molecule. Okay, so you have a cis alkene. Okay, now we're going to move on to hydration. Hydration is with the addition of water. Now, water, I always consider to write it like this, HOH, as if it has two parts, the hydrogen ion and the hydroxide ion, and you'll see why. So whenever I have an alkene or an alkyne, okay, we're going to also keep in mind Markovnikov's rule. So what I'm going to do is I'm going to draw one propyne here, just as I've done previously, and I'm going to add water. So plus H2O, or as I mentioned, I'm going to write it as HOH. The catalyst here is some sort of strong acid, so we just usually use square brackets with an H plus, okay, hydrogen ions indicating acid. What we're going to do is we're going to keep in mind Markovnikov's rule. This hydrogen goes to the carbon that has the most hydrogens already attached to it. So in this case, it's going to go to carbon number 1 because this primary carbon has 2 hydrogens attached, whereas this carbon only has 1 hydrogen. So remember Markovnikov's rule, I always keep in mind the rich get richer. And what we mean by that is the carbon that's already rich with hydrogens gets richer with hydrogens. The OH will then go to this carbon here. So what we end up making in this case as our major product, okay, the OH goes to this carbon. The hydrogen that gets added goes to the first carbon, and we make some sort of alcohol group. So we can name this as 2-propanol or 2-hydroxypropane. There's a couple of different ways that you can name that. And you apply this same rule if you were to use an alkyne to add water to it. The last one are combustion reactions, and you may remember this from grade 11. Combustion reactions can be incomplete or complete. What you need is some sort of hydrocarbon, and when there's incomplete, you have very little oxygen available. And when you have complete combustion, you have a lot of oxygen available. So in this case, you would need some sort of hydrocarbon. So let's say that I'm going to use propane, and I'll just do the molecular formulas here, plus oxygen. When it's incomplete, you're going to get 4 products. And again, you need some sort of ignition source. So I'll put a little triangle there to indicate some sort of heat. You will get carbon dioxide, you will get water, but you also get 2 other products. You get carbon monoxide as well as solid carbon, soot. So these would all be gases, okay, due to the high amount of exothermic heat reaction, and then this carbon would be a solid. What you'd want to do is you'd want to go back and balance that. But again, this is that sort of lethal compound that's made, carbon monoxide. That's not good when you have incomplete combustion. When you have complete combustion, on the other hand, you only get 2 products because you have a lot of oxygen available, and I'd have to specify whether there was a lot or little, and you just get gaseous water and carbon dioxide made. And again, you'd want to go back and balance those. So those are some organic reactions that you should know. And we'll do some practice with some of the worksheets coming up.